Our next panel is titled Tech for Scaleup. I'm excited to introduce this panel to you. They're moderated by Anna D'Alessio. I'll leave it to the panelists to introduce themselves. There's Anna. Hi, Anna.
Hi.
Hi. We're excited to have you. So I'll just let the rest of you get up here. We'll make sure that everybody gets on. Let's see. Hi, Adeola.
Hi,
Addie, actually. I'm going to do Addie this week. All right, is that everyone?
Just one
more. Kirby, right? Yep, there's Kirby. Awesome. All right, I'll leave it to you guys, you ladies. Thank you.
Thank you.
Thanks everyone for joining. We're excited to have this great set of panelists today to talk about tech for Scaleup. And just along the way, if you have any questions, feel free to write them in the Q&A and we'll try and get to them before the end of the session. So I think we should just start with some introductions. Like Amy said, my name is Anna D'Alessio. I work for Ivaldi Group, which is a startup based in California, helping companies shift to digital distribution and using additive manufacturing to produce parts on demand. And so I'll be moderating this panel today, and I'm going to ask all the panelists just to introduce yourself. So Addie, do you want to start?
Yep. Hi, I'm Olubamiji. I am the Director of Additive Manufacturing Solutions at Desktop Metal. My area of expertise at Desktop Metal is binder jetting, pretty much industrialization and scaling up of binder jetting. Thank you.
Becca, do you want to go next?
Sure. I'm Becca Crabb. I'm a software engineer and manager on the software team at Carbon. I'm currently working on our design engine product, which helps users create lattices and design lattices for products.
Thanks. Gabrielle?
Yeah, hi everyone. My name is Gabrielle Thelen. A little bit about myself. My degree is in mechanical engineering. I work for nTopology, which is a software company based in New York City.
Yeah.
Hi, my name is Yan. I'm working for the National Institute of Standards and Technology. So we are developing measurement science for additive manufacturing. My specific area additive manufacturing data management, data analytics to accelerate AM adoption and deployment.
And Kirby?
Great, I'm Kirby Freeman. I work at Carbon. I've been at Carbon about 6 years, working as a product manager for the software team. I work really closely with Becca, and we've announced in the last year that we are helping folks design parts with our design engine product that does latticing and has the start of the metamaterials library.
Great, thank you. So to start out, my first question is, when preparing for Scaleup, what does readiness look like? Or what does that process look like? Addie, do you want to start?
I believe when we're talking about readiness for scaling up, most people just usually think I'll buy more machines, and maybe I have one machine before, then I'll make it two, or I'll buy a bigger machine. But when you're doing readiness, especially when you're trying to scale up, there's so many different processes that you have to think about. And before you are ready for scaling up, you have to have developed that technology to some extent. So you have to have something in place for developing a product. At that point, you must have taken that product from design stage to actually qualifying the product. And now you can scale it. That is one piece. There are other pieces that involve, such as workforce planning. If you're trying to scale up, maybe you had one machine, now you want to scale up to 10, you have to think about how many new employees do I need? At this point, when I'm done with my development, should I be hiring more technicians and operators instead of hiring more scientists? Because the scientists are probably required for more of the development phase. So should I be phasing them out into other projects? There are other things such as quality that is very paramount. You want to make sure that when you're scaling up, you have to make sure every product that comes out of your line what are you going to use to make sure that the products are actually the same quality over and over again? So quality is very critical. Apart from that, you want to scale up. Are you ready when it comes to facility preparation? Are you going to buy a new facility? Are you going to scale up that facility? There is a lot that has to do with facility planning. Now you have to think about waste disposal. In our case, with Minded Jetting, you may have scrap parts, green state. You have to think about the legislation for your state. So many things has to be done when you're thinking about scaling up. My point here is scaling up is beyond, I want more machines. Scaling up involves many processes, and you have to sit down with your team to plan the capital for scaling up, and usually it's beyond just the machine. You have to think about the type of software. For example, ordering software. Maybe before, when you're developing, you're not placing any order, you didn't have an ERP, CRM, or MES system. All of this have to come to play for you to actually be ready to scale up your manufacturing process. And I feel like for me, pretty much, it's a solution, right? It's not just about the machine. There are processes, there is so many things involved apart from the machine. So you have to holistically plan a scale up for it to be successful the way you want it.
Great. Thanks.
So add one more thing, I think a good example of where to look at if you're thinking about scaling up additive is probably start with an MRL matrix. Out there, we have manufacturing readiness plan, and this is available maybe on the NASA website, DoD website, where you can at least have a template, be able to look at some of the processes they're recommending that you think about before scale up. That could be a good starting point. If internally additive is pretty new to you guys, it could serve as a blueprint you can adopt for your process. Thanks.
Thank you. So, Yan, do you feel that the standards and regulations that are in place and being developed right now are helpful or are ready to help us with basically what Addie was just talking about in terms of scaling up?
Yeah, I just want to say that I'm not an industry stakeholder in the AM community representing the standards community. I did find the demands for standards by working with other industry partners. So, for example, on the ASTM F42, so that's for the additive manufacturing, more and more demands for the standards indicates. So I think the scaling up that transformation is happening, especially including small and medium business. And from another side, I will see more specific to my own domain. More people are interested in integration. So I think it's a good signal to see that. So AM, from the standalone system, from a prototyping tool, so moving up to the production industrializing. And I think some of you probably are familiar a little bit with the typical manufacturing automation and management software, for example, MES software. So it has been applied in the traditional manufacturing for years, right? So at the very beginning, we see the focus of the tools on the design and also specific testing. Now we can see that there's more and more MES software for AM. So it's kind of emerging. At the same time, we see the other big competitive companies like Siemens, like PTC, they're all starting to incorporate modules of AM design or AM specific, analysis into their product offering. So that's what I feel, it's a right moment to see, the scaling, this transformation is really ongoing. But standards is kind of always behind technology. So we are catching up, especially on F42. We have a faster balloting process, actually try to prepare the enabling standards for the maturity of the technology and adoption for production.
Great, thank you. So how is software helping to enable customers to be able to design for additive manufacturing so that we can see these parts being used in production? Becca, do you want to start with that one?
Yeah, so I think software can be used in the whole process of this of additive manufacturing, starting with early design, and then I think Addie and Jan both mentioned, I think Addie mentioned ordering parts is another piece of software in this ecosystem, and Jan mentioned MES, kind of quality tracking on the backside. So there's a whole wide range in how software can help move this industry forward and help scale it up, if you will. Some things to highlight on the design front are things like helping users design features that can only be made in additive manufacturing, right? So things that can't be injection molded, but play to the strengths of additive manufacturing, having software help users automatically add those things into their parts. Another one is latticing parts. So as Kirby and I mentioned, we work on software that helps users lattice their parts. And this is another kind of superpower of additive manufacturing that can help designers meet certain performance specs, or maybe even improve on existing performance specs of a material such as foam by using kind of a metamaterial additive manufacturing lattice. And then kind of on the automation and manufacturing side, there's things software can do, such as automatically adding serial numbers to the digital models as they get printed for kind of connecting this digital thread and seeing which printer made which parts in which factory at what time. And things like APIs. So we have an API that is being used right now in the thermoforming industry to help customers automate more of these things and really scale up and increase the throughput of the number of parts they can produce. So automating the packing the parts onto a build and queuing the builds to printers and running an efficient factory through the use of automation is another way that software can really help scale things up.
Great. So speaking about software, Gabrielle, how have you, do you have any examples of how you've seen customers and other organizations utilize nTopology software in order to help with Scaleup?
Yeah, that was a great segue, Becca, into my side of things, the software. If you've ever heard of nTopology, you may have been like many others who first come across us and think that we're just a cool lattice tool, which we are. Don't get me wrong, the speed and scale and complexity of what we can achieve is truly unmatched due to how we represent geometry. But we go far beyond just latticing. nTopology is a tool that looks to remove bottlenecks in your design tasks, tackle your engineering problems, and ultimately streamline processes. I think a really great example of where I've seen this actually in industry is our work with Lightforce Orthodontics. So Lightforce is a company that offers an online portal where orthodontists can upload 3D scans of patients' mouths and determine the position of each individual bracket of a wire brace. And by shifting from legacy software to nTopology, the engineers at Lightforce reduced their design time, I believe, from 10 hours to 3 hours. And to bring this design time down even further, they leverage nTopology's ability to interact with the command line. And now they can execute this entire design process for each brace programmatically using scripts. And they've brought down this design time down to 10 minutes. So this is one of many examples of how we've removed bottlenecks and have automated processes. We ultimately remove the time spent on tedious and manual operations and allow engineers to really better spend that time dedicated to innovating and ultimately scaling up your organization within the industry.
That's pretty cool. I mean, that's a huge change, and especially when lead time is a big issue, to be able to reduce that design time and make this part so quickly is pretty awesome to hear. So Kirby, you've been working at Carbon for a couple of years now, and I'm curious if you've noticed any major changes over the last few years that you find encouraging in terms of leading towards scale up, whether that's within Carbon or just within the industry in general.
Great. Well, I'm going to let everyone hear in on a secret. You're only going to hear it on this panel. We've been in a global pandemic in the last, well, that's had lots of negative impacts. I think for additive, it's made conversations about using and scaling up additive very real. And I think all of our companies are feeling this impact. I'll talk about an example at Carbon, working with Resolution Medical. really to show the power of additive to move quickly, to make better performing parts, and to have a much more nimble supply chain. So this is a class 1 medical device, nasal pharyngeal swab. Before the pandemic, no one was imagining using additive or lattices to make these swabs. And in the course of 30 days, we were able to do a number of design iterations and a clinical trial with major medical institutions like Beth Israel and Stanford, and get approval for this swab. So really the design process and the validation process moved incredibly quickly. And then in this process, that swab was better performing than anything existing. So faster cycle, better part, and then a much more nimble supply chain. So there were factories that were not getting orders the month before, were not producing swabs, and were able to scale up to making millions of units. So global pandemic, wouldn't have chosen one, but pretty exciting about the conversations and the real production use cases that are coming out of that.
Yeah, for sure. It's been really great to see the additive manufacturing community sort of step up over the past almost 2 years now during this pandemic and try and help with new solutions. So that's really great to hear. So what industry or application of additive manufacturing technology do you think has the best potential for scaling up, both from a technical feasibility perspective as well as cost effectiveness? I'll start with Yan. You're muted.
So I'm working with in the standards community. So the most actually I'm working with are from aerospace, and but the conference I attended can include like automotive, medical sector. So through my own analysis, I kind of feel, because these three industries are quite different of adopting AM. So I think for the aerospace, that's the spare part issue, a lot of repairing stuff, and for medical, that's to support the personalization. That's a major thing, as Kirby mentioned. And for automotive, that's the pursuing the performance, like by lightweight, and also consolidate the parts to instead of assemblies. These are the three industry I kind of familiar, and also observe like combinations of like jewelry industry and clothes or fashion industry. So they are kind of might not be the high performed like a metal based, the powder bed fusion based process. So instead maybe polymer or some other process, more cost effective, less tolerance requirements. So that's just I'm not a first hand industry participant, so I would like to hear more from other panelists.
Does anyone else have other thoughts on what's ready? Go ahead, Eddie.
Yeah, I have a few thoughts. So when we're thinking about technology that has feasibility for scaling, in the past, I had worked on polymer. So DLP for polymer is a very good one because of the ability to mass produce. And for metal, binder jetting today is leading. And it's because of his ability to mass produce, really. But I also see laser powder bed fusion, depending on your industry, what type of pad quality do you desire? What's the criticality of that part? Where does it belong in your engine? All of that, the technical requirements should drive what technology you should focus on. So binder jetting may be like high throughput. The question is, does it serve your part accordingly? But if you have parts that fit into binder jetting, I think its property allow it to be high throughput. And there's some other good qualities that you can get out of binder jetting, such as we don't have support structures that are attached to the build plate. So you can stack up a lot of parts within one build bed, and which could drastically reduce your cost. And when talking about cost, not only the stacking up will help you reduce cost. For binder jetting, in our case, our desktop metal, we use mint powder. And MIM powder is already available today. The supply chain is wide because MIM is existing, and the cost of the powder is drastically low. So that means the cost of your part can be really low. For example, I used to work in automotive, so cost of part in automotive are usually very cheap, and the parts are usually large scale. So you need hundreds of thousands. So it could be ideal for automotive suppliers to look at binder jetting because it can mass produce, can do high throughput, and the cost can be really reasonable. And when we're talking about materials, you can get that cheaply because you can get tons of it because they're already available. Now, there are other qualities that I think makes binder jetting really, really good. One of them, apart from design flexibility that everybody has, is the isotropic property that you get. So compared to laser powder diffusion, that isotropic property could enhance your mechanical property. That's critical. In addition to that, we don't use any sort of laser that could degrade the powder. So our powder are usually 100% recycled, so you can keep recycling it forever, which means that also will help you manage costs to a large extent. Some of this quality makes binder jetting very attractive. If you're looking for high throughput, if you're looking for low cost, it could be the right technology for you. If you're actually thinking about complexity as well, because we don't have support structures that kind of could get into a hole and will be had to remove, that may be a good one for you when you have very complex shapes. So it could be good. It has its bottlenecks a little bit here and there, but when we look at the gain you get from it, it supersedes the bottleneck. Every technology do have one. So I'm voting for binder jetting for metal additive when it comes to really scaling up. But for us at Desktop Metal, scaling up, we understand scaling up to one company could mean 10,000 parts. To another company could mean 100,000 or 1 million parts. So we have wide range of additive machine that can cater to whatever scaling up means to you. If you part range, we have machines for that. If you have the millions of parts per year, we have machines for that, and usually support you with hand-to-hand solutions. So we don't just sell you the part, we support you with our expertise so you're able to develop and scale over time, pretty much. Thank you.
Thanks. Are there any other thoughts on that? On the polymer side or design? No? Okay. What are some examples of products that you've seen that have been better than existing products because they were specifically designed for additive manufacturing? How about we start with Becca on this one?
Yeah, so I bet Gabby could join in here too, but I'll start it off with, again, one of Additive's superpowers is the ability to make complex geometries that aren't possible to injection mold or possibly not possible to make with any other technology. And we can take advantage of that new freedom in design to innovate and improve on existing products. And so I'll use the lattice example again here. So we partnered with Specialized, which is a bicycle cycling company. And they've made a couple saddles using lattice structures using our technology. And one is called the Roman Evo Saddle. And the focus on this saddle was on the damping and energy recovery characteristics to protect blood flow and relieve pain when sitting on the saddle. And we use lattices to create kind of a multi-zone lattice. So we have different performance characteristics right around the sit bone than other parts of the saddle. And using that kind of control that lattices and these complex geometries give you on the performance of the part, we were able to reduce the peak pressure up to 26% on the sit bones compared to foam. So I don't know if you've been on a long bike ride, but there's nothing worse than an uncomfortable bike saddle. And another good example that's kind of in a similar space there with lattices is our partnership with Rydell. So again, we used software to help design these lattices to design a directional lattice that has better impact absorption when football helmets head-to-head collisions. And these helmets performed better than previous helmets on the market. So those are just a couple of examples, but I think there's a lot when you look at what new design freedoms additive manufacturing allows you to explore.
Awesome. Gabrielle, do you have anything you want to add?
No, I think, again, this ties into something that we talk a lot about at nTopology, field-driven design. So there's really these three pillars that we talk about here that set us apart from other tools out there. It's the way we represent geometry, implicit model, repeatable, reusable workflows, which I kind of talked to earlier, but then field-driven design. So this is kind of the aspect that takes a little time for people to wrap their head around, but once we get it in your heads and you start the wheels turning, it opens the door to great complexity. So give you a little rundown of what exactly field-driven design allows us to do, and how I've been seeing in industry is basically, field-driven design is a design methodology that enables engineers or designers to leverage valuable data within an organization and incorporate it into a part. Simply put, fields allow the designer to have complete control over that geometry in extremely intricate ways in order to fine-tune their design to get closer to that optimized part. So examples of this that Becca actually was talking to are like, maybe we're looking at a helmet and looking at impacts, or maybe we have a heat exchanger on a helicopter and we want to run a thermal analysis and we're seeing areas where we need to dissipate heat more. So maybe in that case, I want to increase the periodicity of a gyroid lattice based on where I'm seeing hotspots. Or maybe I'm designing patient-specific shoe soles and I'm taking pressure maps from different people and I'm saying, okay, in higher pressure, I'd probably want more support. So let's do that. Let's fine-tune the lattice to create a more stiff response due to high pressure. Or maybe in low pressure, let's have a more cushioning effect. So using field-driven design, we're able to architect the material and really fine-tune it to optimize its performance. So ultimately, we can collect all this important data that we capture within the engineering design process and unify it into a single high-performing part. And I think this speaks to engineering as a whole and how it's always been a very collaborative field. So you have the design side, the materials side, simulation, manufacturing, maybe standards. And I think the people on this panel with our different expertise and backgrounds is a statement to this. So let's not waste this knowledge and expertise, and let's synthesize all this valuable data, and we can do this with field-driven design.
Yeah, it's really cool. So as we talked about how, parts are designed for additive manufacturing, and this might be very new for companies and users, how do you think parts will continue to be qualified over time as we start to scale up? Will it continue to be sort of individually as these parts are looked at as unique parts, or do you think that we can move towards what we're sort of looking at more traditionally based on Six Sigma for mass production? Yan?
Yeah, I have a quick one. I think it's challenging. Okay, depends on the application. So for critical applications, the qualification reliability is challenging because we are talking about 99.9969. Okay, that reliability is needed to fly a part. But maybe in other, if you just make non-functional parts, so all in the fashion industry, that might be less critical. That's what I think in that mass production, probably the traditional Six Sigma qualification still works, but still that requires some, standards, new methodology change and demonstration or proof. For example, today's, especially for aerospace, FAA, right? So guided. So the qualification is very, very, strict. So NASA has its own qualification standards for their component, and FAA has similar. So you have to qualify material first, then you qualify your process. So you lock your process parameters. Then you basically you have to qualify a master product. Then you can make more copies, right? So basically compare all your copies of data then to the qualified part. So you do one by one, yeah. This is kind of purely experiments based, okay, for each step, material qualification, process qualification. So now the new way people talking about called equivalency based or probability based. So that is heavily rely on data. accumulate data from all the life cycles, material, machine development, part development. So part could be from material coupons, and a coupon actually testing doesn't approve, the geometry shape you manufacture. So, but the combination of all this data, so which is not original designed to be full factorial. So, but based on machine learning, transfer learning, some advanced, machine learning technology, the hope is, so we can find a process envelope, a process strategy, give us the best possibility to have a qualified part. But still, I would say we can maybe reduce the experiments down to 50%. I still kind of feel people rely on data or simulation itself to qualify, critical applications. Yeah, that's just my thoughts.
Mm-hmm. Yeah, I mean, I think that it's really interesting to hear what sort of tools already exist that we should be relying on in order to qualify those parts versus trying to conform into what we're used to doing in some of these industries. But I'm curious to hear if you think that it's sort of the same between polymers and metals, or if you have sort of different opinions on how that process would look. I don't know if Kirby or Becca, you want to start from the polymer carbon side?
Yes, certainly on the metal side, not what we're thinking about yet. But I'm excited to be on this panel and see us all in these disciplines. We have at Carbon felt the urgency that I see in this panel for the innovations possible with additive to get out into the world and to have more engineers be able to access them. And we think and have always prioritized sort of maybe the foundational part of our offerings to create a digital thread. Additive really can start and be digitally native, and we believe that extending that thread, adding to it, making it accessible, provides such value for designers, for hardware companies, for contract manufacturers, for consumers. Becca and I were just talking with an internal colleague, and I loved the way he said that there are, at least 4 layers of novelty in additive manufacturing, and whatever we can do to add to the transparency and confidence and control that is possible around polymer or metal additive manufacturing, the more we can let engineers access the technology. So we believe the digital thread and letting all of the different consumers and participants in the ecosystem be able to add to it and use it to characterize the results. Their additive can be faster, the amount of data can be larger, but I think there are so many exciting companies working on making sense of that data, feeding it back into the manufacturing process to make better parts.
Great. Are there any other thoughts from the metal side, or even thinking about sort of qualification from the design perspective before you even get to producing a physical part?
I can add a few things there. For metal right now, I think I wouldn't say there is a particular software that you can plug in a part that is going to help you with, oh, this is printable or not. Why? Because we have several processes. And what we're seeing today is a lot of attention is being paid to laser powder fusion, right? And if that is what everybody's placing the attention on, there are different feasibility rules for all this different technology. So what will print well on laser powder fusion may not print well on binder jetting. So I think there's no software on the market today that can really satisfy everybody, except if people are building their own internally. Now, I feel like every process design guideline, a design guideline that would help us know that if you redesign this for additive, you introduce this topology, you optimize that geometry. Is it printable? For us, we use sintering processes as well. Is it printable? Is it sinterable? We have to make sure before we go ahead. Yes, you would have redesigned it. Maybe it looks like there's functional improvement. But if you get to that printing process, your part keep breaking because maybe it's too thin or you can't depowder accurately, all of the functional gain that you think you have is not going to come out because you would have no output. So I think right now everything is still majorly experience based, I would say, until we get to a point where software is able to help us decide that all of your optimization will lead to a product that can, at the end, is printable, is centerable, and when we measure it dimensional wise, everything still look good. Right now, the type of software we could really count on are the ones that can help you decipher whether you should move on. So it could look at the size of your part and say, this is too big for the platform you've selected, so these can be printed on that platform. Or it could look at some of the features to kind of criticize it and say, this looks too bulky on this side, or this has some type of edges that we don't print, reject, or go modify. But the modification and all of that still have to be done by somebody with a lot of experience. So we don't have softwares like right now that is smart enough, especially on the MindJet side, that is smart enough to help us take already good design that have been defined towards where we're going. On our side for Desktop Metal, yes, in the beginning of the process for design, we have design guidelines. So we provide our customers with that. So before you give us any part, please read that document so you have some idea of what we can print and what is feasible at our hand. And when your part comes to us, we evaluate it. And if it meets the criteria, we may move forward, or we can come back with some suggestions on what should you change for us to be able to feasibly give you a good product. Now, internally, we have something similar to Magics that we use for build prep called MFG. And we also have, for us, sintering is our biggest bottleneck. When it comes to whether the part will succeed. We can print the part. We can depowder it successfully because we have good grain strength. But can you sinter it adequately? So we have a software called LifeSinter, which is still part of design. So before you print it at all, LifeSinter can run a sintering simulation to tell you that this part is going to what? It's going to bend, it's going to distort. If you orientate it this way, maybe you should change it this way, or maybe you should add some meat over here, some stock over here, so that you can improve its sinterability. So we have something to at least help us make sure that if we're going to fail, there is prediction that this particular area is where you could have failure, so you can mitigate that. On the design side, we're using that a lot, but that only happens after we have kind of talked to you, let you know that's going to be printable, change it a little bit, and we can provide you that feedback alongside change it here and there for you to know that centerability, you have to kind of beef it up in this area or remove some things in that area, or we may change orientation based on what we work on our machine.
Mm-hmm. Yeah, I think I really like what you said, that it's still a lot experience based, that not just anyone can come in, learn how to use software, press a button, and we're going to have repeatable prints across the board. So that's good to hear. Gabrielle, do you anything?
Oh, go ahead.
Sorry, Becca.
I was going to just add on to that. I think Addie said something really spot on about how like every process is different, and so there's no kind of one software that designs for all of these things. And so I think Carbon, with the design software that we're building, obviously we have the benefit of being very tightly connected to Carbon's printers and our printing platform, and so we can kind of focus first on trying to solve these problems that Addie was talking about. You know, identifying areas that might not print well, running simulations, optimizing design to be able to print faster, all these kind of things, and can start with the printing platform that we know best, and then over time expand to other platforms as those platforms mature and their processes, you know, are more easily codable for and easy to write algorithms that can help design for.
Yeah, just like to piggyback off this because I think this is really, really interesting. Again, going off what Addie said, like knowing what your constraints are. I think when I'm training users in nTopology or kind of giving demonstrations, we can create a lot of really complex geometry, but it's not really great if you actually can't manufacture it or get to the printer. So actually knowing those constraints there's things that we can bake into the software through like topology optimization. We have like an overhang constraint, and you're only going to get a result that complies with that overhang constraint. But if you're doing other latticing operations, maybe I'm applying like a bunch of like a stochastic lattice or Voronoi lattice, and I have a bunch of beam thicknesses or pore sizes, knowing your constraints. Okay, I can't print below a thickness of so forth, and maybe I can't print above a thickness of so forth, or maybe I have to think about different overhang angles of this lattice. Well, we have filters within our software that allow the user, if they know those constraints, can filter out those things from the design. So it's not, let's create this geometry and we get a green check and we're going to go print it and then throw it on a helicopter or something. No, there's a lot of more design intuition that goes into it. And again, more collaboration amongst the manufacturing side, the material side, and so forth.
So it looks like we have one question from participants right now. So this is for you, Addie. How are the challenges different between laser powder bed fusion, which is lower volume and more expensive, versus desktop metal, higher volume and cheaper in terms of workflow and process performance?
Challenges. All right. One very obvious challenge that is different a lot is where the heat is applied. So for laser powder fusion, it's layer by layer, apply the laser, and it's eating that surface. And you could have residual stresses, which could lead to cracking or some issues layer by layer. And that also allows you to form anisotropy kind of material properties. On the binder jet side, our heat is applied after printing. So the printing is using the raster based. You just pour the binder on the powder and it glues it together. So there's no heat applied at all. And you can handle that. But once you take that into the sintering furnace, where you're supposed to actually now melt a part of it, depending on the process you're using, that is where heat is applied for us. And that is where we experience discussion. That is where we have tons of issues, cracking, and all of that. So those two technologies, the point at which it is applied really does differentiate them in terms of challenges. You can deal with that one in the machine, but you can't deal with the other one until you get a sintering furnace. It tests what the situation is. So somebody can tell you and say, hey, it's high throughput. Yes, it's great, but there is still sintering constraint. If you print it properly, you have enough expertise to actually sinter it properly. Another challenge is support structure. So for laser powder fusion parts, they have support structures attached to the part. And when you're done, you have to find a way to break the support structures. It could be labor intensive. And if you're dealing with a lot of parts, so you need to go through that labor intensive process. For binder jetting, it has a different type of support structure. So it has sintering setters. You can just remove the setter if it's grain setter, or you can just use ceramics, which is reusable. So the two technology are so different that what affects them they're so different. Now, when it comes to getting 99.99% properties, you can get that on laser powder fusion. You may not be able to get that on binder jetting. So they cater to the same different audience because of the different, I would say, pros and also cons. It's just a little different, pretty much. Yeah, high volume is great, but its own constraint is pretty much a lot of time the bottleneck of sintering, and laser is just a little different in that case. I hope that helps.
Great, thank you. So I see Amy joined back again, I think, because we're running out of time.
Yes, thank you all so much for this really awesome panel. I wish we could just go on and on, but unfortunately we're out of time. If everyone could join us at the main stage for some final remarks, we'll do that now. And thank you all so much again.
Thank you.
Thank you for having us.
Thank you.